All right, guys, so we've talked about the idea of Newton's first law, that an object at rest is going to remain at rest, and if it's in motion, it's going to remain in motion with constant velocity. But what I want to talk about today is this very end part, and that is all true unless that object experiences a net external force. So I want to talk about how we could determine what that net external force might be. And so what we're going to do here is we're going to look at an example of the question, and I'm going to basically go through some of the steps on how you might determine the net external force that is acting on a particular object. All right. So I'm going to go over to my document cam, and we are going to look at an example here and see if we can figure out how to get the net external force. So this particular question tells us that Derek leaves his physics book on top of a drafting table. Now, what a drafting table is, you guys, it's essentially a table that can tilt. All right, it's able to tilt, like architects use these and that kind of thing. So it's inclined at a 35-degree angle. The book has a weight of 22 newtons. The table exerts a force of 18 newtons perpendicular to the table's surface, and friction acts along the table's surface upward with a force of 11 newtons. And then it tells us it wants to determine the net external force acting on the book and whether or not the book will remain stationary. Okay, so to do this, I mean, when they start throwing all kinds of forces and angles and that kind of thing at me, I know I'm going to need a diagram. You've got to have a diagram here to kind of keep track of all of this stuff. And so right off the bat, they tell us that we're working with a drafting table here that is inclined at a 35-degree angle. So that's the very first thing I'm going to kind of write in here. I'm going to say that this is my drafting table. Okay. And they're basically telling me that this angle right here is 35 degrees. Okay. Let me, you know what, I'll pull back just a little bit so we can get a little bit more of that diagram in. Okay, so I know that this is inclined at 35 degrees, and they tell us that a book's sitting on top of it. So I've got a book here sitting on this table, and they tell us a few things about this book. The first thing they tell us is that the book has a weight of 22 newtons. Now, this weight, and what we do with these force diagrams is the forces always emanate from the center of the object that we're talking about. So this tells us we have a weight of 22 newtons, okay? And we know that weight, this is basically the force of gravity acting on this book, is always straight down, okay? So that weight is going straight down. I'll label this the force of weight, or F sub W, and we know that this value is 22 newtons. Okay. They say that the table exerts a force of 18 newtons, which is perpendicular to the table's surface. So if this is the table's surface, then this force that's perpendicular to it is going to go off in this direction. And we know that this particular force, they've told us, is 18 newtons. All right, so there's the second force written in. And finally, that it tells us that friction acts along the table's surface. So friction is always going to be parallel to the surface that you have contact along. So it's going to be parallel to the tabletop. And it tells us that it goes upward with a magnitude of 11 newtons. Okay, so these are the three forces that I have acting here. It doesn't mention any other force. And what this wants to know is, it wants to know what F net is. So that's what they're asking us for. And then later on it asks whether or not the book's going to remain stationary. So this is a fairly complicated question. And so I'm going to go through some steps on this so that hopefully you guys can kind of see how you might go about solving this. I will tell you that you're going to get more practice on this later on, but this is your kind of first taste of it. So kind of watch for the steps is what I would say. So the very first thing that I want to do, stepwise, is I want to get a force diagram in here. And that we have. We have these three forces that are here. I'm going to go ahead and label these. This is called F, N, actually I use a capital, or we call this the normal force. You'll learn more about this as we go through this chapter. This, of course, as I mentioned, is the force of weight, which is gravity pulling you down. And this one here, I'm going to call it F. I'll just call it FF, the force of friction. Okay? I made a mess out of that. Okay, anyways. Once we've done that, the next thing that I'm going to want to do, anytime I get a question where it's on a surface that's not horizontal, this would be far easier if this was a horizontal surface, but it's not. So what I do is I'm going to rotate my coordinate system. So what the heck does that mean? Well, a coordinate system is like your XY axes. So, I mean, if I think about this, that would be my y-axis. And if I take another pen and set it on here, that would be my x-axis. The problem that we have if we do it this way is, in the end, what I'm going to have to do is figure out what my components of those forces are that are in the x direction, and what components of these forces are in the y direction. Now, here's the problem. If I look at these forces without rotating my coordinate system, I have one force that's in the y direction, and that's the force of weight. However, if my coordinate system is like this with x and y, okay, if I look at the frictional force, that 11 newtons, it's got a little bit of x and a little bit of y. If I look at this one that's 18 here, it's got a little bit of x and a little bit of y. And so I would have to break up both of these into x and y components before I could really do anything with them. And that's work. That's a lot of work. If I take my coordinate system, however, my x and my y here, see if I can do this. You know, I'll try holding them off to the edge. I'll take my x and my y and I rotate them until my x is parallel to that tabletop and my y is perpendicular to it. Notice that instead of having two different vectors that I would have to break into x and y, I really only have one, the force of weight. And so the reason that we would rotate this coordinate system so that instead of x lying like this, it actually lies like this, is to make this easier. So in red, I'm just going to kind of put a dashed line here. And this is my new x, all right? That's my x coordinate. And if I do the same thing here, that's going to be my new y axis, okay? So again, if I think in terms of steps, I would say number one, diagram. If you don't get the diagram right, you're probably not going to get these questions right. Second, rotate. Your coordinate system. And I'll say if necessary, okay? You may not have to rotate it if it's not at an angle like this one was. All right. Next thing you do, break up your vectors into x and y components. So again, if I look at the forces that we have here, I can see that this one is totally in X. Again, our new X, our rotated X, that friction is totally in X. I don't need to break it up. All right, you do not need to break up a force that is already in either X direction or Y direction. So I don't need to break this up. This one here, the normal force that's going up here, I don't need to break it up either because it's totally in Y. Okay, so I got one vector that's already totally in X, another that's totally in Y. That's why we rotated the coordinate system, so we don't have to break both of these up. And the only one that I need to worry about breaking up then is this force of weight right here. So this force of weight is going to need, because it's neither in X or totally in Y, it's actually a combination of both, okay? And so in the end, what I'm going to need to do here is I'm going to need to break this up, where instead of thinking of this as a single force of weight, okay, I need to think about it as two vectors. One that is parallel to Y, and another one that is parallel to X. And so I would call this component of the weight, again, the weight we know is straight down, 22 newtons. I would call this FWY. It's the Y component of this vector here, the hypotenuse. And I'd call this one FWX. Again, the X direction runs this way. So this would be, if it's parallel to that, we would call this the X component of the weight, right? So we need to break those up. The thing is, in order to figure out what FWY and FWX are, I need two things. I need a side, and I need an angle. So I need to know what both of these are, both this angle and this side. And while I do have a side, I don't seem to have an angle. But I want you to kind of envision what happens here. Let's say that I took this drafting table, which is capable of being tilted at different angles. I took this drafting table and I started to decrease the angle of the drafting table. Okay. Now, as I decreased this angle, as it came closer and closer and closer to being horizontal, I want you to envision what would happen with this weight. Remember that the weight always points straight down. It always points straight down. And so as you start to tilt this, the weight continues pointing straight down. But what's going to happen to this angle as you start to realizing that FWY is always perpendicular to that tabletop? It always is. So as I bring that angle down, notice that the angle FWY, once it gets totally flat, FWY is parallel to that weight. And as I go back, notice what happens to the angle. It gets bigger and bigger and bigger as I go back until finally at that what was the angle on this? 35. At that 35-degree angle, it's in this position. So the way to think about this is, if I start from horizontal, each degree that I go up, FWY increases its angle at the same rate that you increase this. So as you tilt up, if I go 1 degree up, the difference between the weight, which always points down, and FWY is going to be 1 degree. If I go 5 degrees up, because this stays pointing down, but FWY is going to have its angle increase when I go to 5 degrees, it's going to be 5-degree difference in angle. So this works anytime you get this situation that whatever this angle is that your surface is at, it's the same as this angle right here, because this always points down and this always points perpendicular to that surface. And so if this is 35 here, that's 35 there. Now, hopefully you follow the logic. If not, just remember that when you do this kind of a question, that 35, whatever your angle is of the slope, it's always going to be this angle here because of the fact that weight always points straight down. okay? So we now know what that angle is. So if I want to break up those vectors into x and y components, it's really not too tough. FWY, if you look at it, this is the adjacent side to that angle, and I know the hypotenuse. We'd use cosine here. So we would say that cosine of the angle, this is SOHCAHTOA, cosine of the angle would equal the adjacent side, which is FWY, divided by the hypotenuse, which is 22. Okay, CA basically, cosine equals adjacent over hypotenuse. If I rearrange that to solve for that adjacent side, it would simply be cosine of the angle, all right, cosine of the angle, times the hypotenuse, which we know to be 22 newtons. All right. We can do the same thing for FWX, except in this case, FWX is the opposite side from the angle, so we would use sine here instead. So we'd say sine of 35 times the hypotenuse, which is 22 newtons. Okay? So at this point, I can actually figure out what these two are. I need to go grab my calculator, though. So I will be right back. Okay, I'm back. So doing these, I'm going to say cosine 35. Make sure that I'm in degrees. So we would say cos 35 okay, times 22. Okay, I get 18.02. And nothing happened to the units, so that would be in newtons. We do the same thing here, except we're using sine now for FWX. So I would say that I have 35 degrees, and I want the cosine of that, excuse me, sine of that, times 22. And I get 12.62 newtons. Okay. So we've done this step. These are the only two. These two vectors here, FWX, or excuse me, FWY and FWX, are the only components that we had to break up, because this was the only vector that wasn't totally in X or in Y. So once you've broken up the vectors, and you could have 3 or 4 vectors that you need to break up, but once you've broken those up, your next step here is to take the sum of all the forces in the X direction and the sum of all the forces in the Y direction. So again, you guys may not remember what the symbol is, but this is sigma, and it simply means you are adding all the forces that are in the X direction, you're adding all the forces here that are in the Y. So I need to take the sum of the forces in the X direction. Well, what are those? If we look at our diagram, what are the forces? I'm going to pull back just a little bit, give us some room. What are the forces that are in the X direction? Well, if I look at this, I have 2 of them. I've got FWX is in the X direction, so I would add FWX plus the other force that's in the X direction is this force of friction that's going up the slope. Okay, so I would say plus the force of friction. Okay. Now, let's think about these numbers, though, because if I look at, I have values for all of these. If I look at this force here, FWX, it's going down the slope towards the right. But friction is going up the slope towards the left. So when I add these together, one of them is going to have to be negative because they're in opposite directions. So I'm going to call the down the slope forces, or FWX, I'm going to call those negative. So then to get the sum of these, I would basically have negative FWX had a value of 12.62, okay, newtons, plus my other force was 11 newtons. So that gives me the sum of the forces in the x direction then are going to be equal to negative, what, 1.62 newtons. Okay. Now, what about the sum of the forces in the y direction? Well, those forces are FWY and this normal force that's here. And once again, if I look at these two, I'm going to end up with one going upward and one going downward. And so I'm going to call FWX, or excuse me, FWY negative. That was 18, I think, 0.02. Plus the upward force was 18. Now I will tell you, these are newtons, both of them. I will tell you that this 0.02, this is simply a calculator rounding thing, okay? Really what these should come out to, or be extremely close to, is 0 newtons. Think about why I can make that statement though, you guys. If my y is going this direction, perpendicular to the tabletop, how do I know that this has to be 0? Well, think about what would happen if it wasn't. What if I went ahead and solved this and I had a negative force in the y direction? Well, that would mean I would get a negative acceleration, a downward acceleration of that book as it slid down the table. That would make no sense. I would never observe that. That would basically be the book dissolving into the tabletop as it moved. It would fall downward in the y direction as it moved down this slope. I've never ever seen anything like this. And I would say if you did, I mean, you may be on some kind of hallucinogenic pharmacy subscription or a prescription or something. It wouldn't make any sense. I mean, I've never seen a book sink into the tabletop as it slid down. That never happens. I know that has to be 0. Well, that basically, my 5th step is combine your sum of your forces in the x and your sum of the forces in the y direction. Okay? Now, that basically means that I've got an x force that's downward and a y force that's 0. So I really don't need to combine them because one of them, excuse me, one of them is 0. So there's no connecting head to tail when one of them is 0. But if you did have a net force for the y, and you'll see some later on, we would have to combine them head to tail and figure out what the resultant was. But in our case, we can basically say that this combination of those two forces, the combination of these is your net force. So in our case, we would say F net equals negative 1.62 newtons. And I would say the direction on this is down the tabletop. Hopefully that makes sense to you, okay? So this thing is going to have a net force that is down the tabletop. So think about what this would mean. Let's say that I knew what that net force was. If I know what this net force is, and it's down the tabletop, what's the book going to do? Because this is really the second part to this question. It asked us, let me pull it down a bit. It asked, determine the net external force, did it, and whether or not the book would remain stationary. Is that book going to remain stationary, folks, if you have a net force acting on it that's down the slope? It won't. This thing's going to, it's a different color. So I'm going to say the book will accelerate downslope. Okay? The book's going to accelerate downslope. That's going to be what happens. Okay? So this book is going to accelerate downslope. Now, this doesn't have anything to do with this question. I'm pretty much done with this example, but think about this. If this book's going to accelerate downslope, you're going to see, I'm going to introduce to you guys in the next day or two, Newton's second law, which basically says that if you know what the force is that's acting on something, F equals the mass of the book, which we could figure out here, times acceleration. So that means if I knew the mass of the book and I knew what the force was, which I do, I could calculate the acceleration that this book would experience. Okay? If I knew the distance from where it's starting to the end of the table right here, this distance here, I'd have a delta x. If I knew what delta x was and I knew what a was, okay, if I knew what these two were, I could calculate the change in velocity. I could calculate the velocity that this book was moving at the moment it left the table. Now maybe you guys see where I'm going with this. I don't know, but hopefully you will in a second. If I know how fast it's moving when it goes off the table and I know the angle that it's moving at, I could determine what its initial velocity was as it fell to the ground. So I could actually, by simply knowing how much force is acting on this, I could actually determine where, kind of do a bullseye here, where on the ground that book is going to hit. See, all of this stuff, you guys, is related. All of it is related to each other. So we don't tackle forces and motion separate from projectiles and one-dimensional motion. It's all basically part of the same beast, is what we would say. And as we learn more and more, we can start to make these attachments between these different areas that we're learning about. Okay, so this is how we would determine a net external force. And because we had a net external force, we would say that this book that's up here is no longer going to be first law in it. First law basically says object at rest stays at rest. This guy is not going to stay at rest. It will accelerate down the slope because you have a net external force that's acting on it. All right, that's it for today. We're gonna do a little bit of practice on this tomorrow, so you guys will get some time to kind of work into this. All right, okay, that's it. Have a great day, and I'll see you guys tomorrow.